Hello everyone, my name is Yuan-Chih Chen, and today I'm going to present our research on diffusion or non-diffusion adversarial defense, rethinking the relation between classifier and the adversarial purifier. This study focuses on explaining the generalization gap between classifier and the adversarial purifier. The motivation behind this work is to find the drawback of widely used diffusion-based adversarial purifiers. I will begin by explaining the finding briefly before moving on to our methodology results and the conclusions. In contrast to most prior studies that focus on diffusion models for test-time defense, our work investigates the generalization laws introduced by diffusion models on classifiers. We find that while non-diffusion-based purifiers may appear simpler, they actually demonstrate strong adversarial robustness, and more importantly, they excel in different transferability and color generalization, all without relying on any additional data beyond the original training set. This perspective allows us to rethink the relationship between the classifier and the purifier, and to better understand the limitation of diffusion-based defense in maintaining classifier generalization. Here, I want to show the discrepancy between the diffusion-based purifiers and the classifier. The two circles represent the difference between purifiers and the classifiers. The red circle draws the generative domain of the purifier, while the blue circle represents the true prediction of the classifier. When the input image X is from the training set or a similar distribution, for example, test data split from the same dataset, it has a higher likelihood of maintaining clean accuracy. However, if the input image X prime is an unseen sample that the classifier can correctly identify, diffusion-based purifiers are more prone to misclassification. For example, a brown cat image in a training dataset can be classified very well, and the purified version of the image can also be classified. However, if a blue cat not included in the dataset, the classifier can also predict very well because the generalization caused by the data augmentation and the model structure used by this classifier. And the diffusion model tend to purify this broadcast to the improper image. We explain more about generalization loss caused by diffusion models. Diffusion models tend to generate images similar to training data. In contrast, classifiers are trained with data augmentation to enhance generalization and prevent overfitting. Since diffusion models focus on generating natural images, common data augmentation techniques such as color jitter, rotation, and mix-up are typically avoided to prevent the generation of unrealistic or unnatural images. This fundamental difference leads to a discrepancy. Classifiers leverage data augmentation to learn texture variation, improving their ability to classify unseen images, while diffusion models push unseen images toward the closest point in the training distribution, which may not align with the classifier expectation. On this slide, we illustrate the distribution of purified images to explain why diffusion-based purifiers can reduce clean accuracy. In this figure, consider an image that the classifier can correctly recognize, even though it differs from the training data. For example, it may have a different color tone. We refer to such samples as corrected images, which are shown here as the orange distribution. As the diffusion time step increases, the diffusion purifier gradually pushes these corrected samples toward the clean data distribution. However, this process can inadvertently cause a mismatch between the purified image and their original corrected input, leading to a drop in clean accuracy because the purifier effectively overrides natural variations that the classifier have learned to handle. This illustrates how diffusion-based purification can unintentionally harm classifier generation rather than improve it. Here, we present a real purified image to support our findings. Diff-Pure, Mimic Diffusion, and Score-OPT are representative diffusion-based purifiers, while DDA is another diffusion model designed to restore corrupted images to their clean counterparts. As we can observe, Diff-Pure, Mimic Diffusion, and DDA noticeably alter the fine detail of objects like the banana, kiwi, strawberry, and bread. Score-OPT, on the other hand, tend to inject excessive noise during purification. This distortion, though visually plausible, can actually degrade the classifier's accuracy as they disrupt the original image semantics. In contrast, our MAP effectively preserves high imagery quality and maintains semantic consistency, achieving purification without sacrificing classification performance. On this slide, we present the image quality matrix, including PSNR and SSIM, to illustrate how diffusion-based purifiers tend to degrade clean images. As shown in this figure, diffusion-based purifiers achieve only around 20 dB in PSNR and less than 0.75 in SSIM, indicating a noticeable loss of the image quality after purification. In contrast, MAP preserves image detail much more effectively, achieving significantly higher PSNR and SSIM values, which confirm that our method can maintain visual fidelity while still providing robust defense performance. It is evident that recent diffusion-based purifiers, such as Diff-Pure, Score-OPT, Mimic Diffusion, significantly alter image detail during the purification process, whereas the purification loss-based approach effectively preserves more of the original image detail while maintaining robustness. Simply altering the reverse process of diffusion-based purifier by introducing randomness or estimation can significantly increase semantic loss in the image. Our proposed method, the Mask Autoencoder Purifier (MAP), is optimized using two loss functions. The first one is the purification loss, which guides the model to transform adversarial images back into clean image, ensuring effective defense against attacks. The second one is the reconstruction loss, designed to preserve semantic content and visual quality. This loss helps maintain consistency between the purified image and the original clean image, thereby reducing the discrepancy between the classifier and the purifier. Together, these two objectives enable MAP to achieve both robust purification and high fidelity image reconstruction. For our experiment, we use ImageNet and our newly created color ImageNet dataset. The color ImageNet dataset was generated by applying color transformation to the original ImageNet image. Specifically, for each ImageNet from ImageNet, we randomly sample 10 different color styles and perform style transfer to obtain diverse color variations. All experiments were conducted under consistent conditions. We use ResNet 50 as the baseline classifier to measure the performance of a pure classifier without any purification process. In the bar chart, the blue bars represent the results on imaginary, while the orange bar correspond to the color imaginary results. The figure on the left illustrates the drop in clean accuracy, and the figure on the right shows the drop in robust accuracy. From the result, we can observe that MAEP exhibits smaller accuracy drop in both cases, indicating better robustness and color generation. In contrast, the diffusion-based purifier suffer from larger performance degradation, particularly when facing color transformations. In this experiment, we evaluate the effect of image corruption using Imagine A and Imagine A-C. In the figure, Imagine A represents the classification accuracy on original image, while average refers to the mean accuracy across all corruption types. By comparing the accuracy drop between Imagine A and the average, we can identify which purification method is more likely to harm the classifier generalization ability. We observe that diffusion-based purifier experience a larger drop compared to MAEP, which once again supports our finding that MAEP preserves better generalization under corruption. Here are the main results on difference transferability. As shown in this figure, our method demonstrates stronger transferability compared to diffusion-based purifiers. Specifically, even when MAEP is trained on Cipher 10 and evaluated on Cipher 100, it still maintains an accuracy that is close to the model trained directly on Cipher 100. In contrast, the diffusion-based purifier exhibits a significant degradation in robust accuracy when transferring from Cipher 10 to Cipher 100. This result highlights that MAEP effectively bridges the gap between the classifier and the purifier, resulting in more consistent and generalizable defense performance across different datasets. Unlike the previous slide, which focused on different transferability between datasets, this slide demonstrates that our defense can also transfer effectively from low resolution to high resolution domain. Specifically, when MAEP is trained on Cipher 10 and evaluated on ImageNet, it achieves comparable performance to diffusion-based purifiers that are trained directly on ImageNet. Moreover, MAP attains higher clean accuracy because the reconstruction loss helps preserve image quality and reduce the discrepancy between the purified image and the original clean image. These results further confirm that MAP maintains robust generalization across both dataset domains and the image resolution. To summarize, our research identified and analyzed the discrepancy between classifiers and the diffusion-based purifiers. We demonstrate that non-diffusion-based purifiers, such as MAP, can effectively avoid this discrepancy while achieving strong defense transferability. Although diffusion models have shown remarkable capability as adversarial purifiers in previous studies, their limitations, especially their impact on classifier generalization, remain underexplored. Our findings reveal that diffusion-based purification can impair generalization, particularly in cases involving color variation and other distribution shifts. Overall, this work provides new insight into the relationship between classifier and the purifier, and we hope it encourages the community to rethink the drawback of diffusion-based defense and explore more generalizable alternatives. Thank you for your listening.